Hello there. Today we'll look at BLEURT, Learning Robust Metrics for Text Generation by Tibalt Salam, Tipanjan Das, and Ankur P. Parikh. So this paper on a high level proposes a new metric for text generation tasks such as machine translation by leveraging a BERT model to produce like an automated metric, an automated quality metric. And they make this BERT model robust by pre-training it on a very wide array of tasks that they can use synthetic data to train it. And therefore, the model and the resulting score is very robust to shifts in distribution. And they advocate that this could be used in the future to assess text generation systems. All right, as always, if you like content like this, consider subscribing and sharing it out and leaving a like. Tell YouTube that it's good content. Of course, only if you agree. So, what's the problem with evaluation for text generation? So if you know the machine translation community, basically what they do is they have these data sets where they translate from one language into another, let's say English to French. And they have a training data set that is fairly okay-ishly large. And then they somehow need to evaluate this. Okay, so you have like a test data set, but all you can really do is sort of calculate the perplexity of a language model that you produce or of a translation model that you produce. There's not really a metric for translation. So the gold standard is to get it to humans. So you train on this data set, you produce a program, this is your machine translation program that you produce from the data, and you let this run on your evaluation data set, and you give the results to a bunch of human raters. These could be regular people, these could be linguists that are experts in translation in both languages, and they will score each of the outputs of the machine translation systems, and at the end you will get like a number, like 8. Your system is 8 good. The problem, of course, is this process is very, very slow. So the machine translation community does this every year, and it's quite slow and it's quite expensive, as you know, it requires these humans here to assess all of these systems' output. And you want a sort of a sizable output, right? Because you want sort of a good sample of the machine translation system. So this is not really satisfactory, but like an automated score like Perplexity is also not satisfactory. What people have done is they've come up with proxy scores for the humans, and 2 of those scores are called ROUGE and BLEU. And specifically BLEU is one of these metrics that people use, and it takes n-grams in the sentences. So n-grams would be like snippets of, like, let's say 4 words after one another, and there would be these snippets and that the machine translation system produces, and then it would go into the validation data set and look at the gold standard translation that was also produced by humans, and it would also look at these snippets of size 4, and it would just kind of assess how many of the snippets overlap. Of course, the machine translation system has never seen the label, like the gold standard for that particular set, otherwise it wouldn't, be fair. But you basically compare n-grams of output and gold and some gold standard. You can have multiple gold standards and so on. So this BLEU metric is more of like a heuristic, and it has been found to correlate fairly well with the humans up until recently, of course, with the explosion of neural machine translation and especially transformer-based machine translation, I guess, but also their system that use LSTMs with attention. These systems have become extremely good. I don't know if you've noticed, but Google Translate has been getting better and better really fast. I remember the first years of Google Translate when people still made fun of it. I don't think many people make fun of it now. At least it's not a meme anymore. So the better and better these systems were, the more these metrics like BLEU and ROUGE have diverged from the humans. And they're not really reliable anymore, especially if you compare really high skill systems to each other. BLEU tends to not correlate well with humans. And therefore, we're looking for a new metric a new metric that correlates well with humans, but can be evaluated automatically. And this paper here proposes this BLEURT. Now, can we just stop with the variants on BERT? We get it, you use BERT for everything, but you know, yeah. So they say it's a learned evaluation metric based on BERT that can model human judgments with a few thousand possibly biased training examples. Okay, so what you would do in these cases is now the creation of a metric becomes a machine learning task itself. So what you'll have is you'll have a data set of things that are gold standard translations by humans. You'll have the output of the machine translation system. Okay, you put them together. So you have the gold standard sentence. This would be the optimal translation. You'll have whatever the machine translation produced, and then you'll have a human look at it and create a score, like this 8 right here. So it says these two sentences, they match 8 good. Okay, so 8, maybe it's out of 10. So this bottom thing is a very good translation for the top thing, like to match the top thing, or the human assesses the quality of the sample. And now you have a training data set, right? You have a Z, they call, I think this Z and Z tilde or something, or Y. Yes, this is zip. They call this Y, which is the gold standard label. This is Y tilde, whatever the machine produced, and or X tilde, and then Y is the label. So your task is now, given X and X tilde, predict whatever the human would say about this. Okay, so if you can collect a few of these samples right here of different machine translation systems, then you can make a data set out of this, all right, and formulate a machine learning task. And that's exactly what these competitions have done. So it's like a meta competition now. It's a competition for designing the best metrics of the other competitions, basically. And of course, the difficulty here is that the data set isn't static, because if you come up with a metric such as BLEU, let's say you come up with a better BLEU, you would want these other tasks to use it in the next years as well, because the thing about metrics is you need to be able to compare to like previous years and so on. So you would want a metric that is still valid for other years and other slightly different tasks, and also for other machine translation systems. So if you just learn on data from this year's competitions, and in 5 years all of these models will have become so much better and they'll produce different output, and that's the difficulty. Your metric should still be valid at that point. And this paper basically deals with the fact that, can you learn such a metric from data that exists at one point in time that will be robust to shifts in distribution? So in 5 years, the machine translation systems, they're better. They maybe use different language constructs to translate certain things because they assess that better. Can you still make a good judgment about which of these systems is better than the other system? Can you still assess how humans would rate these systems? And they're saying that they found the method to do this. This BLEURT, as they said, not only have they found the method, but their method only uses a few thousand possibly biased training examples. And they do this via a new pre-training scheme. So they say a key aspect of our approach is a novel pre-training scheme that uses millions of synthetic examples to help the model generalize. Now, why is it important that it only uses a few thousand training examples? Because these are generated by humans, right? And humans are expensive. So, and it's not like ImageNet, you do it once, you have it for 20 years. This is done year after year, and you need real experts, like translation experts. So this is expensive. So the fewer of these actual training examples that the thing can be efficient on, the better. So they circumvent this by using, they say, millions of synthetic examples to help the model generalize. They do this in a pre-training step. They say BLEURT provides state-of-the-art results on the last 3 years of the WMT Metrics shared tasks. Now this is this meta task where you're asked to come up with a metric for the other tasks, and the WebNLG Competition dataset. In contrast to a vanilla BERT-based approach, it yields superior results even when the training data is scarce and out of distribution. All right, so let's have a look at what they do. Okay, so they say, what do we need to do to fine-tune BERT for quality evaluation? Now, if you don't know what BERT is this, it's basically a model that takes in a bunch of text. So you have a bunch of text, and then it's a model that is a transformer. I've made a video on it if you want to check that out. And then you get, as outputs, you get like a sequence of vectors, but important most of the time is only the first one, which you then use in a subsequent task. For example, if you want to do classification, you would put a classification layer on top to classify it into certain classes. If you want to do regression, you do that. You can do other things with these outputs right here, but for this particular paper, only this CLS output is relevant. Okay, so you would input this pair of gold standard and output of the machine, and the output would be a output Y, which is either a number or a class label. And in this case, it's a number. Okay, so you input right here, you input these two things, and out comes this whole sequence, and you take the CLS output vector and you put it through a linear layer right here, weights and bias, and that would output a number Y. And the number Y you train to be as close as possible to what the human would say about this pair X, the gold standard, and X tilde, the output of the system. Okay, so this is what you would do if you were simply going about it. Just take BERT, take the model. So BERT's really good at language, right? Take the model and train it on this data set. They say, however, fine-tuning BERT requires a sizable amount of IID data. Okay, we don't have that in these tasks, which is less than ideal for a metric that should generalize to a variety of tasks and model drift. So the problem with just applying BERT here is that, well, they say it, you don't have enough data, and it won't be a robust solution. It will only work for this particular data set that you train it on. The solution, they say, is you pre-train on synthetic data. So what does that mean? They say the key aspect of our approach is a pre-training technique that we use to warm up BERT before fine-tuning on the rating data. And you might know BERT training, which is where you do this masked language model pre-training, right? So if you are given a piece of text, let's say you're given this piece of text right here, what you would do is you would drop out a couple of words like this one, and ask BERT to reconstruct it. So like a denoising autoencoder. And that way BERT learns sort of about language in this particular way. Now, they're not saying you should replace that. What they're saying is first you should do this masked language model pre-training. Second, you should do their synthetic pre-training. And third, you should do the fine-tuning. Now, if in the naive approach, you would skip this step 2, right? So their claim is that by introduction of this step 2, that you could be a lot better and a lot more robust, because you've already had you're already exposed to information in this step that would make you more robust to distribution shifts in this fine-tuning data later. Okay, now I've short interlude right here. I've advocated for this step to be called priming. Because otherwise you always have to say like, okay, I want to pre-train BERT, but I don't mean like pre-training. Like I don't mean this is already called pre-training. I want to pre-train after pre-train. So I just vote for this to be called priming. I have no idea. Like if you come up with stuff like this, probably you've heard it somewhere. So I guess I might not be the inventor of this, but it is a good sounding word and it sort of fits, right? Okay. So they say we generate a large number of synthetic reference candidate pairs. So what they're going to do is they're going to take a bunch of text, and in their case, I think it's Wikipedia. And for each Wikipedia article, they're going to, so they take Wikipedia, they're going to draw sentences or samples or paragraphs from Wikipedia, and these are going to be your Z, and then they're going to kind of muddle with them a bit. They're going to disturb them a bit, to make them a bit different, to make them go Z tilde. And this simulates the difference between what the machine translation outputs and the gold standard sentence. They're usually not exactly the same, right? If you translate a sentence, there are many ways you can do it. And their goal is to sort of produce a data set that has sentences and sort of perturbed versions of the sentence, but not perturbed like randomly, but perturbed in a sort of language knowledgeable way. Okay, so how do they do this? They have three different ways. First of all, mask filling with BERT. So what they're doing is they take a BERT that can do language modeling, right? A pre-trained BERT, and let's again say we have this text right here, and they simply drop out 2 words or so and fill them in again with BERT. Now, BERT might produce the same words, or it might produce slightly different words. Depending on how many you drop out, you can choose the kind of amount that you perturb these sentences. Okay? So the second is they back translate. So what they do with back translation is they use a machine translation model. Now, it doesn't matter which one you take. They use any machine translation model to take a sentence, Z, and then they map it to another language, say from English to French. So this is Z French, and then they map it back again. The Z tilde is now the French to English translation. So you need 2 translation models. First you translate it to French, and then you translate it back again. And that would sometimes give you the same sentence, but often it will give you sort of a paraphrase of the sentence that you had at the beginning. Okay, so that would be the second version, that you could make pairs of sentences that are sort of similar. And the third way is just to drop out words. They just found this to help. Okay, so now they have a giant data set of sentences and perturbed versions of sentences. So what are they going to do with that giant data set? And the answer is they're going to take this Z and Z tilde, and you're going to put that into BERT, into their thing that they prime now. This is the priming stage, right? This was pre-trained on masked language modeling. Now they want to prime it. What are they going to do? They're going to take this CLS vector. And now, of course, this is not the final task, and we don't have final labels for these 2 things. So we need to somehow come up with our own tasks and labels for them. And they decide to go a whole bunch of tasks. So they go like, I think, I don't even know, they go 8 or so or 5 or so different tasks. They construct different tasks to perform with these 2 things. And this could be metrics like BLEU or ROUGE, or this BERT score right here. So you simply calculate the n-gram overlap between Z and a Z prime. That would be one of the scores. It could be the back translation likelihood, which is how likely does a back translation model assess this sentence. oh, here is all the things. Six different tasks. Okay, so 6 different tasks. And the catch here is, so what would happen, for example, with BLEU is you would take a model and you would calculate the BLEU score between those two things, but you wouldn't input that into BERT. You would ask BERT to predict the BLEU score. Okay, so BERT would be outputting B hat, and B would be the actual BLEU score. So you would train BERT to predict the BLEU score of this particular pair of input, and so one you take as like the input and the other one you take as the reference. Okay, and you would ask BERT to predict the BLEU score of this, to predict the ROUGE score. You would ask it all of these signals, you ask the same model, you ask to predict all of these scores for these two things. Okay, so you can calculate all of these scores by either BLEU is like a script you run, or you have some other model, like a pre-trained translation model that you use to assess the, that you ask how good is this in terms of this particular task, back translation, and then you try to predict that score. Where it's important, you're not training the model to perform these tasks. These tasks, you already have another model that's specialized to these particular tasks, and you simply ask them to score the input. Okay, you have an entailment model that outputs how much does the second sentence entail the first. That basically means, does the second sentence follow from the first? And of course, this is not, it's not actually proper input data for that task, but you can still ask the model. And if these are good translations of each other, if these sentences match, then the second one should probably follow fairly well for the first. But at least you can, if you make BERT predict that, it will learn something useful about the relation between the two sentences. So the entire name of the game here is to come up with tasks that if BERT learns to predict the score of these tasks on those inputs, on pretending one is the input and the other one is the output, or on the two inputs and then trying to predict the score, then BERT would learn something useful. Okay, so that's the trick here, is to come up with these pre-training tasks, and you train them all at the same time. And by doing it all at the same time, and by doing it on many different perturbations on these different tasks, you hope that your model learns something. It's kind of becoming attuned to the variations that language can have and what it needs to pay attention to. And then you hope that if you then have done this, then take this model and then do step 3, which is fine-tuning on the actual data you have. You would guess that it becomes very good at that data, but also it retains all of these abilities and generalizes better to other sort of distribution shifts. All right, so that is the thing here. And they, on this task, on this metric learning tasks, they do outperform all other models right here. And what I find interesting is down here, where they now test for the distribution shift. So what they're saying is, okay, this is all on data basically where, we train on training data and evaluate on testing data, and they're sort of the same. They come from the same year, from the same machine translation models, and we don't really know how, next year the machine translation models might be different. Does our score still hold? So they try to simulate this by splitting the data, and they introduce this skew factor. So what they'll do is they'll split the data. So usually, as you can see right here, the training data, the ratings, these are the human ratings. The training data is sort of distributed like this would be the test data, and the training data would almost be overlapping that. If you can see like the dotted lines right here or so. So you can see the overlap between the test and the trained data of the human ratings is very close. Now they say we can skew that. We can sort of filter the data such that in the training data, only very bad sentences are, and in the test data, there are only very good sentences. Okay, and this simulates the fact that this might be the previous year's data that we train our metric on, and then we evaluate it on the next year's data where all the systems have become better. And what this does is, you can see right here, the bottom axis is the test skew, and the color here is the training skew. Okay, so what we're interested in is to the right and down the colors. So as this skew increases, you can see right here that the quality of the metric decreases. Okay, the correlation with the human ratings decreases, but it still remains fairly well. But especially the training skew, if you update the so if you make the training examples really bad, so to say, the score just drops down. And they can show pretty well here that if you add this pre-training, then the score, except in this extreme case, so the score for all of these, it remains relatively high, and especially remains above the BLEU score, which is always sort of worse, right? So this is pretty neat and shows this power of this pre-training, basically. That's the robustness to quality drift metric. And they have a bunch of other metrics right here where they ablate and so on, but I don't want to go too much into that. I more want to make some comments on this work. So what I think. So first of all, in a paper like this, what I would like to see is like the extrapolation right here to if and where this ever crosses the BLEU score, right? Because I mean, okay, it seems like, yeah, this skew of 3 is a big number, but who knows if 3 is a big number, right? We can't assess that. What we need to see is really the crossover point between the models to assess where is it no longer valid and so on. The second part here is that my problem with this method of splitting the data, I mean, yes, okay, you split the bad from the good, but it's not only that these things are getting better. So right now everyone's using transformers for everything. Everyone's using BERT for everything, right? And BERT is a specific architecture that is going to be good at specific things, at specific grammatical constructs in specific languages, right? So the mistakes it makes are very systematic. Now, if in 1 year or 2 years, all of a sudden a new model pops up, I don't know, like someone discovers that graph neural networks are really good at machine translation. These models are going to be attuned to a very, very different set of constructs. They might be better overall, but they're going to make a different sort of mistake. And so I think just assessing the skew via just dividing up the data into bad and good ratings, I don't think that covers these distribution shifts that they set out to cover, right? What I would have expected is something like them, because these tasks are repeated year after year, and I would have expected them to, for example, train on 2017 and then evaluate on 2019 or something like, or show, like evaluate on 2017, 2018, and 2019, and there we would have a much better assessment of a distribution shift over the years, right? So it is not super convincing to me. And what is most worrisome is if you look at their pre-training tasks. I mean, okay, there's BLEU and ROUGE, but there is BERT score, right? There is entailment, which is also a BERT model, and the back translation. I mean, who knows? That's probably either going to be a transformer or a LSTM with an attention mechanism, which is the attention mechanism is the basis for transformers. So all of these things are basically going to make the same sort of biased mistakes, right? They're going to it's not like there is Gaussian noise on top of these things. All of these things are going to be weak in the same sort of assessments and not agree with, like, they're going to have systematic errors in them with respect to them predicting the human scores. And if we evaluate our systems that some are also using exactly that thing, right? So the systems we evaluate, they are using the same type of models as here. They're going to fall prey to the same type of mistakes. And then if we switch over to systems that use some different, right? So next year we have some systems that use different techniques. They're going to be like exactly maybe not bad in these particular things, but bad in other things. And then this thing will output a systematically biased assessment. So it's sort of a house of, like, if you've seen these images of plugging in the power strip into itself and you have infinite power, it's like, it's very, to me, it seems very dangerous to have such an overlap of architectures and methods to evaluate systems as you have in the systems themselves. But I hope this will be regularly checked with human scores and assessed as to how much these systems are out of sync or in sync with humans. All right, this was it from me for BLEURT. Check out, they have the code available, the metric is available, evaluate your stuff with it, and bye-bye.